welcome to lecture 3. In the last class we were looking at the equivalence between full rate sampling and time interleaved sampling. The motivation to consider time interleaved sampling is those applications where implementing a full rate sample and hold might just not be possible. So just like if you are not able to work hard enough, you hire more people to do the same job. Here the idea is to use 2 sample and holds, sampling at half the rate and working in parallel, and somehow you stitch the outputs together in order to get an output sequence which is what the full rate sample and hold would have given. You understand? And so as shown here, this is the equivalent of the full rate sample and hold, right, and this shown below is the mathematical equivalent of time interleaved sampling. Please note the words mathematically equivalent. Physically it will not be implemented like this. Okay, what makes more sense to implement in practice is that the top sample and hold channel will be sampling at all even multiples of the sampling clock period, and the bottom channel will be sampling at all odd multiples of the sampling period, which is t. Okay. To analyze, it does not make a difference if we have a mathematical equivalence, which is why I simplified things by sampling both of them at the same instant of time. However, one is artificially been advanced by a time t, and if we put this whole contraption inside a box, the system inside the green box should in principle be not distinguishable from a full rate sample and hold, right. And during the last class we wrote down the expressions for spectra at various places in the system. What are important are, let us get some more intuition on this by actually plotting the spectrum. Last time we had equations for the various spectra. Let us now plot and get some intuition. Let us just quickly remind ourselves what is the maximum bandwidth of the continuous time input signal x of t which will allow us perfect reconstruction. I mean, please note also that we in the last class we denoted 1 by t by fs, correct. So let us quickly remind ourselves again, what is the maximum bandwidth of x of t which will allow us to enable perfect reconstruction? Fs by 2, alright. And in the interleaved sampling system, what are we sampling each channel at? No. Please note, this signal x of t can have a maximum bandwidth of fs by 2, and in this interleaved channel, each of these channels is sampling at what rate? It is also sampling at fs by 2. You understand? So the signal, so as far as each of these channels is concerned, the input signal bandwidth is fs by 2 and the sampling rate is also fs by 2. So what do you think happens in each of these individual channels? They will be aliasing in each of these individual channels. However, from end to end we saw that the system is equivalent to a sampling system operating at fs. So if there is aliasing happening here and aliasing happening in the lower channel, but when you add the two, if it is equivalent to something where there is no aliasing, what must be happening? What must be happening is somewhere along the line the aliased components are cancelled. Okay. So let us simply take a look at the spectra and plot them again and plot them this time. Last time we saw this through the maths. Let us actually draw pictures and convince ourselves that that is indeed happening. Okay. So Can somebody please remind me what we called these to be consistent with notation used last time? What did we call this point? Okay, so this was called point C, all right. What about this point? G for God. Okay, so we call this G, and what did we I guess we must have called this A then, and then B, C, D, E, F and G, and H is the final output. Is that right? Okay. So I am not going to go over all the math again. At C, the spectrum must be of the form 1 by 2 T sum over all K x of Fs by 2 pi times omega minus pi k. All right, and at G we saw last time that the spectrum is 1 by 2 T sigma over all K x of Fs by 2 pi times omega minus pi k times e to the power j minus j k pi. Does it make sense? These are results that we derived the last time around. So now let's sketch these. How do you let us say this was the continuous time signal, and let us assume that the continuous time signal is occupies the entire Fs by 2, right. So if this signal was ideally sampled at Fs, then there would be no aliasing, correct. However, how does this look like? It is shifted by, so let us remind ourselves again, if this signal was sampled at Fs, what would the discrete time spectrum look like? What do we do to get from continuous time to discrete time? This is a continuous time signal. First you make copies of and paste at what intervals? At Fs, right. So if we had sampled the original signal at Fs, this is what we would have got. Okay, and then we replace the x axis with, we scale the x axis, we multiply this by 1 over t, and we scale the x axis. So what does Fs by 2 become? Fs by 2 becomes pi, this becomes minus pi, and so this becomes 3 pi, 5 pi and so on. Right. What is this in the discrete time domain? This is what we would have got this is omega minus 2 pi k. This is stuff that we already know, okay. But what is this expression? What is the difference? I mean, what is the difference between this expression and this expression? One is repeated at 2 pi, whereas the other one is repeated at at pi. So, how do you think this expression will look like? You will have aliasing terms now repeated at, you will have images repeated at pi. Okay. So, you will have right. So, this corresponds to the spectrum at C. Is that clear? Now, I need to find this or draw the spectrum at G, but before we go there, please note that indeed we see aliasing in the top channel, right. The spectrum at C itself is aliased, and this makes sense because the signal bandwidth is fs by 2 and we are sampling at fs by 2. Now, let us draw the spectrum at G, and to do that I will copy and paste what is the only difference between the spectrum at C and the spectrum at G? The ones which you have shifted by pi are now inverted in sign. So, instead of having I am sorry, does it make sense? Here also we note that there is aliasing, correct, because the sum of the spectra is the black guy plus the red guys. Okay. So, there is aliasing in both channels. However, when you add C and G together, what is happening? The step and repeat happening at odd multiples of pi get cancelled, whereas those at the even multiples of pi reinforce each other, and what we get eventually is this, and we also understand that this strength is 1 by 2 t, this strength is also 1 by 2 t. So, when you add these two, the strength will be at proportional to 1 by t, and you get the result at h is a spectrum like this, which is what we expected in the first place, given that this whole system is equivalent to a system which samples at rate fs. Is this clear? Now, the next thing is to figure out what happens when there are non-idealities here. So, let me copy this again. As I said, a practical realization of this approach would basically have two sample and holds, one sampling at all odd multiples of t and one sampling at all even multiples of t. Then you have these two sequences and you interpolate up by a factor of 2 by inserting zeros, then move one of the sequences by one sample and add the two. Okay. There are several practical non-idealities which come in, which we never accounted for in the derivation. For one, as I mentioned that day, the signal is passing through different channels and each channel can add offset. In other words, the output here, for example, is not simply the sampled output plus some offset, which we denote by V offset 1 and V offset 2. Right. So, the first non-ideality we consider is offset. Now, let us try and understand intuitively what we should expect for the output sequence if each of these channels had different offsets. Or before you go to different offsets, maybe we try to figure out what happens when they have the same offset. So, when both of them have the same offset, what do you think will happen to the output? If all the channels have the same offset, then the output will simply be the ideal output plus the offset that each channel is added, correct. Now, let us try and figure out what happens when the two channels have different offsets. What do you think will happen? How do you think the output will? I mean, let us try and understand this by putting 0 input, right. If you put in a 0 input to the system, ideally what should you see at the output? Ideally we should see 0. If both channels had the same offset, what would you see? You would see a constant DC value of V offset. Now, if both channels had different offsets, V offset 1 and V offset 2, what would you see? So, very good. So, in all even samples, you would see offset 1. and all odd samples you will see offset 2. Mind you, the offset stays constant, so every alternate samples value will be the same, correct. So if you look at this sequence, what can you decompose this as? Can you see something in this sequence? Can you comment on the spectral content of this sequence? This is a discrete time sequence. Please note that this is a discrete time sequence. By definition, it only exists as a sequence. So there is no, I mean the, so I mean, at what frequency? Please note this is a discrete time sequence. So it is, there is no, there is no question of frequency is fs. You understand? That was continuous time. After sampling, you only have a sequence. So whatever frequency you come up with must be within the range 0 to pi, correct? All right. So now can you look at this sequence? In general, it's very difficult to look at a sequence and tell you, I mean, say what its spectral content is, unless you have a natural Fourier transform inside your eyes. You understand? Okay. But for this special simple sequence, we should be able to look at it and say, and this is one channel offset, this is the other channel's offset, all right, and this is V offset 1, this is V offset 2. Is this clear? V offset is a constant which is added to every sample in that channel, correct. See, if the input was, if this input was grounded, what would we expect ideally at the output? All zeros. Now what is happening is that each channel is adding a constant but fixed offset. I mean, it's, I'm sorry, it's constant offset to all samples. So instead of being, instead of the output of this channel on the top being 0 0 0, it is V offset 1 V offset 1 V offset 1, but these are only the even samples. This channel on the other hand also adds offset, but its offset is not the same as the offset added by the first channel, and this can happen in practice due to mismatch in the circuits that I use to implement these systems. So let us not worry at this point about where these offsets are coming from and why they are different. Okay, we just take them for granted that this is what would happen in practice. Now the lower channel also adds offset, which is V offset 2 V offset 2 V offset 2 and so on, and since we are interleaving these two sequences, it follows that the output of the composite system when the input is 0 will be a sequence like this. Is this clear to everyone? Okay. Now all that I am saying is that we can think of this sequence as the sum of two sequences, one which is the average drawn in the blue squares, correct, plus another sequence which is what How does the other sequence look? The difference here I will denote that by triangles. Here what is the difference in the second sample? Negative, and these two will have the same magnitude, correct, because by definition I have removed the average. Okay. So, this is the average, which is V offset 1 plus V offset 2 by 2, and the amplitude of this sequence, which as we can see is periodic with a period of 2 samples, is the peak to peak amplitude is V offset 1 minus V offset 2. Okay. Since the discrete time tone is periodic with 2 samples, in the frequency domain it must be at a sinusoid at omega equal to pi. Is this clear? So, now if we trace this back to the continuous time domain for ease in understanding, we can think of this tone at omega equal to pi as coming from a continuous time sinusoid operating at, it is like if you see a tone in the discrete time domain at a frequency omega equal to pi, that must be coming from a, we would normally think that that would be coming from the continuous time input at what frequency? Fs by 2, correct, because if we put this whole thing in a black box and we look at the output sequence, and the output sequence seems to show DC plus a tone at omega equal to pi, and as far as we are concerned this is coming from a sample and hold operating at a rate of Fs, which basically means that the input must be coming from, must have a tone at DC as well as Fs by 2. In other words, offset in each of these channels will make us believe that the continuous time input has components at Fs by 2 as well as DC, while the real continuous time input is 0. So, obviously this is some kind of error, correct, causing us to get confused about the nature of the input in continuous time. All right. Okay. Now, if the input was not 0, what do you think will happen? So, this causes offset and a tone at omega equal to pi, which corresponds to Fin equal to Fs by 2. Okay. Now, let us discuss what happens when, apart from the offsets, there is a regular input coming into the time interleaved sampling system. What do you think will happen? What do you think the output sequence will be?
The input and offset.
Very good. So, if the input was not grounded, but was a regular input that you would normally use, then the output sequence, apart from containing the ideal output sequence x of kt, would also contain this extra sequence, because this simply adds to whatever was supposed to come out ideally, correct. So, what is the conclusion now? Therefore, What is the conclusion? Yes, so basically if you have offsets in each of these channels, the output spectrum will be the ideal spectrum plus DC offset plus a tone at omega equal to pi. All right. Okay. Now let us think what would happen if instead of having a two-way sample and hold, we had a four-way sample and hold. What do you think will happen to offsets?
Pi by 2 frequency.
Pardon? Is it only at pi by 2? Very good. So if you have a 4-channel sample and hold system, you will see tones due to offset at pi by 4, 2 times pi by 4, 3 times pi by 4 and oh actually I am sorry, no, if what did I say, we assumed, what was this? Okay, so I am sorry, if we have a 2-channel sample and hold, then we see tones at pi. So in other words, it is 2 pi by 2. If we have 4 channels, we would see tones at 2 pi by 4 and 2 pi by 2 and as well as DC. You understand? So in other words, if you translate this into the continuous time domain, a 2-channel system would make it look as if the input contained DC as well as a tone at Fs by 2. If you have a 4-channel system, it will look like DC, Fs by 4, Fs by 2 and 3 Fs by 4, which is the same as Fs by 4. Okay. So in general, if you have an n-channel sampling system, you will see tones at Fs by n and its multiples, and that makes intuitive sense because every nth sample is the same, because the first channel processes the first sample, it is again exercised only after after you have gone through all the other channels. So you come back, every nth sample is the same, right, and the samples from 0 to n minus 1 are all different because they are processed through different channels. So you can always expand this as a Fourier series with a fundamental period equal to n samples, which corresponds to Fs by n. Does it make sense? All right. Okay. So in other words, we already see that using time interleaving has its problems. I mean, nothing comes for free. All right. So we thought we would make our life easy by using 2 slow sample and holds and stitching their outputs together, and we already see that because of offset there is artifacts in the sampled output which would not have been there if the sampling rate was Fs, I mean it was a true full rate sample and hold. Is that clear? Okay. Now the next any questions? Okay. The next non-ideality is gain error. So, let me again copy this and paste. Now, just like each channel introduces its own offset, because these two channels are built using different circuitry, though they are nominally identical, it will turn out that there will be a small gain error. In other words, the gains of all the channels will not be the same. You understand? So, let us now consider gain error separately. In other words, the nominal gain is 1 plus alpha, and the nominal gain is 1 plus beta in the lower channel. Ideally, alpha equal to beta equal to beta equal to 0, both are very small numbers. In practice, alpha will not be equal to beta, again because of random mismatch between both the channels. What do you think? Before we get into the math, let us try and understand intuitively what we should expect. What do you think will happen? If alpha was equal to beta, what do you think will happen? If alpha is equal to beta, there is no real problem, in the sense that it will appear as if the entire sequence of the output is has a gain error of 1 plus alpha, has an error of gain error of alpha, correct, because it is like the even samples getting multiplied by a constant 1 plus alpha and the odd samples also getting multiplied by a constant 1 plus alpha. So, when you stitch the two sequences together, it is pretty much like the original sequence, except that all numbers have been multiplied by this extra factor 1 plus alpha. So, there is no real problem. Now, what do you think will happen when alpha is not equal to beta? Very good. So, let us recall that what were we depending on? So, if the channels had identical gains, then we recall that we are adding the spectra at, and we understand that each of these sub channels is not sampling at Nyquist. So, there will be aliasing in each of these sub channels. However, when we stitch the signals of the sequences together, magically the aliases are getting cancelled off, correct. Okay. Now, if there was a gain error in both these channels, in other words, this, if you will recall, G is the output of the channel on top, H is the output at the spectrum at the output of the lower channel. So, if the gains were different, this is 1 by getting multiplied by 1 by 2t into 1 plus alpha, whereas the lower channel is getting multiplied by 1 by 2t times 1 plus beta. Is this clear? Because all that we have done, we have already computed the spectra at this point and this point, correct. Now, if there was a gain error in this channel, it is simply taking the spectrum at C, for instance, and multiplying it by 1 plus alpha. In a similar fashion, if there is a gain error in the lower channel, it is like to compute the spectrum at G, we just take the old spectrum and multiply it by 1 plus beta instead, correct. So, since a picture is worth 1,000 words. What were we seeing earlier? If alpha was equal to beta was equal to 0, then which of these components were, which of these colors was getting cancelled out? The images in red were cancelling exactly, whereas the images in black were adding up. Now what do you think will happen? If alpha is not equal to beta, there will be a red component. In other words, there will be an aliased component. Okay, so if I so the strength of the black images will be 1 by t plus 1 by 2t times alpha plus beta. The red ones, however, will be, this is somewhat exaggerated, because the cancellation is not perfect anymore. Does it make sense? Okay. And what will be the height of these images? It will be 1 by 2t into alpha minus beta. Clearly, when alpha is equal to beta, again the images cancel and there is simply a gain error, correct. But when alpha and beta are not equal, we see that there are aliased components. Okay. Now specifically, if the input consisted of two sinusoids or consisted of a sinusoid, what do you think will happen? If the input consisted of a sinusoid, the discrete time spectrum would ideally have done something like this. Okay. Now what do you think will happen? I don't really need to draw the periodic extension, because I know it's periodic between minus pi and pi. I'm going to get rid of the scaling factor also, just to make the diagram a little clearer. And what else? What other tones would be present? Yeah, so there would be something here and something there. Correct. So what is, sorry, I made a okay. So if the input was continuous time and had a frequency of let me erase and redraw it clearly. I am blowing up just that region between minus pi and pi. What we would have gotten something like this, and the red part would have done something like this. This is minus pi, this is pi. Now, what I am asking you is what would happen for the specific case of the input being a tone at some frequency f in, right, in which case the input spectrum would, for instance, would have two impulses here, and if the input was at f in the discrete time spectrum, where would they occur at? F in by Fs times 2 pi, correct. And because these alias components do not cancel, there will be something there, all right, and this is f in by Fs times 2 pi. What is this distance? Is also f in by Fs times 2 pi, correct. So, ideally if we had just a sample and hold running at the full rate, which of these colors would you see? Only the spectral component shown in black would appear. Now, because of time interleaving and gain mismatch, we see that there are other artifacts in the spectrum, and they are at what frequency? At high frequency. And what is that high frequency here? Fs by 2. If this distance is f in by Fs times 2 pi, it is pi minus f in by Fs times 2 pi. Translated into the continuous time domain, it is like having an input tone at, so in continuous time it is like having Fs by 2 minus f, okay, or equivalently you can say it is Fs by 2 minus plus f in, because whether you have a tone at Fs by 2 minus f in or Fs by 2 plus f in, when you sample it at Fs, they will, you understand. Intuitively, why does this make sense? So, if you have a tone at Fs by 2 minus f in, why can you tell me why does this intuitively make sense? Yes.
That would appear only at if you alias, if you sample this f in tone at Fs,
Yes.
you would, the aliasing would happen exactly at f in by Fs by 2 minus f in.
I mean, how is it that, I mean, the question I am trying to get at is, how is it that if you sample a sinusoidal tone at a frequency f in with a single channel sampling at the rate Fs, we see only these two tones in black. However, when we use a 2 channel sample and hold with gain mismatch, we see additional tones. Please note that the amplitude or the strength of these tones is proportional to alpha minus beta, correct. So, why does this make sense? Yes,
aliasing is happening,
correct,
because there is a gain mismatch.
They are not cancelling. All right. I mean, that is the math in words. But is there more intuition to this than?
So in each channel you have sampling at fs by 2. So there is a multiplication of a tone at fin and I mean some frequency components at fs by 2 and multiples of that. So multiplication in time domain is nothing but in frequency domain we will have the sums and differences of those frequency components. So here because fs by 2 and fin alpha will have sums and differences.
Well, you are kind of there, but let us see. So if you think of what is really happening, right, ideally we were expecting, let us say, some sequence. The crosses correspond to one channel and the circles correspond to the other. This is, let us say, the ideal sequence expected out of the whole system. Now, because of gain error, what is happening? Every odd sample is getting multiplied up by some constant which is different from unity, and every even sample is getting multiplied by another constant which is not the same as the constant which is multiplying the odd samples. So, you can think of this as taking this ideal sequence and multiplying it by a sequence which is you understand. What is this sequence? This is the ideal output. The actual output can be thought of as taking the ideal output and multiplying it by a sequence where the even samples are 1 plus alpha and the odd samples are 1 plus beta, correct. And just now we said that this kind of sequence, what is the spectral content? It consists of DC and at tone at pi, which in the continuous time domain maps to fs by 2. So, if you take a sequence and multiply it by another sequence which has got both a constant term and a tone at pi, what would you expect for the output sequence? You will see sum and difference of a tone. The tone at pi will beat with the input tone and give you the sum and difference. You understand? That is why it makes sense that you see components at, we see the original spectrum plus some components at pi minus f in by fs times 2 pi. The intuition is that you multiply the ideal sequence with a sequence which has got a constant value plus a tone at omega equal to pi, which is why you see other artifacts. Now, taking this further to an n channel system, what do you think we will see?
You will have n minus 1 components. DC.
So, if n equal to 2, we have components around fs by 2, correct. If you have n equal to 4, you will have components around fs by Fs by 4, right, and its multiples. You understand? Is this clear? So, we will stop here for today and we will continue